It's a good thing that people have been asking about the star formation rate, because I'm here to tell you about, try to convince you that we need radiation pressure in simulations to produce realistic galaxies, or galaxies that not only look realistic at redshift 0, but also grow according to the observational estimates. I'm a graduate student at MSU, and Anatoly is my advisor, and most of my collaborators are actually sitting here.
Extra 10 minutes.
So we have these two problems that we've talked about ad nauseum already in simulations. These are the classical problems. Your gas cools too much, it collapses to the center, forms stars. You get very concentrated spheroids, you lose a lot of angular momentum. So I won't spend too much time on that. We know that if you put in, if you shut up your cooling or you put in more energy from supernovae, you can get rid of those problems, at least at low redshift. But here's another problem that came up recently that people are more worried about, is that the empirical, semi-empirical constraints shows that the star formation rates of galaxies have a very different shape as a function of halo mass. So the higher mass halos have higher star formation rates at earlier times, whereas the dwarf galaxies are just peaking in their star formation activity near redshift 0. And this does not only affect the star formation histories themselves, but you can think of many other things that are affected, such as the enrichment of the stellar populations that we observed at redshift 0, the enrichment of the IgM, the amount of baryons in the CGM, and the ionization conditions in the CGM, for example, as well as the structural parameters of galaxies as a function of stellar age. Here's a slide from the Aquila comparison project, where they played around with different feedback models to try to reproduce a Milky Way at redshift 0. So this is a halo of the halo mass of the Milky Way, about 10 to the 12. And so you see a very clear trend here, where if the models that get the star formation, the stellar mass correct, which are on this side, tend to have earlier star formation history. So this is the time at which most of the half of the stars form. So they end up having most of the star form as early as redshift 5, which is incorrect. Here's what other zoom-in simulations have done over the years. Again, you see the same trend, a very large peak of early star formation. This is both true typically in massive galaxies like the Milky Way, as well as in dwarfs. So you can put in more things and make the problem better or worse. You can put in molecular gas star formation, and you kind of still see the same trend. Even with the early thermal feedback, you still see star formation rates that are too high at high redshift. So here's how we decided to look at this problem in AMR simulations at very high resolution. Here's how we put in the radiation pressure. I won't get into the details very much, but just tell you that this is constrained by stellar evolution models. So there's basically no free parameters. We're in the momentum conserving regime, so we're putting in the minimum amount of momentum possible. And again, this is very different from the early thermal feedback that the MAGIC simulations use, because we're putting it in the form of pressure and not thermal energy. Oscar Agertz looked at the comparison of these two approaches in a paper, and he concludes that you get a very different ISM if you put it in the form of energy versus pressure or momentum. The other ingredient that we have that's slightly different is the star formation. Most simulations worry about reproducing the Koenig-Schmidt relation at kiloparsec scales, whereas we do local star formation. So we form stars where gas is cold and high density at a constant efficiency that we take from observations, which is between 2 and 5%. And here's why that may be important for the galaxy properties. Here's the heating over the cooling rate as a function of star formation threshold. You can see here that as you go to lower efficiencies, the different lines, you get into the regime where you're not heating the gas to temperatures where it can overcome the cooling. So the energy is radiated away. If you put in radiation pressure, you're better off, but still the velocities to which you can accelerate your gas depend on the efficiency that you put in. And as Mark emphasized, this may not be important at galactic scales for ejecting all the baryons out of the halo, but it still may be important for the galaxy inside the halo itself. And here I'll try to convince you that once you reach this regime, you're okay, so you don't care too much about the details of the implementation of the parameters are. So we're trying to answer these questions here. Specifically, in this talk, I'll focus on the star formation histories. And we have two different halos, one which is the size of M33, one which is about a few times 10 to the 10 solar masses. And I'll focus on that one for the, in the interest of time, which we simulate to redshift 0. And the only difference between the models is I adjust the star formation efficiency a little bit. And I run a model with only supernova feedback and 3 or 4 different models with supernova feedback plus radiation pressure. So you have both effects contributing. The fiducial model, as I said before, is the momentum conserving model, in which you assume that the boost factor, which we call tau UV, the optical depth in the UV is 1. And then we run models where we have higher boost factors as well. And I emphasize here that we're not trying to tune these parameters to produce realistic galaxies. We're just evaluating the effect that radiation pressure has on the formation of the galaxies. So you don't have to read the whole table here, but this is the typical stellar mass-halo mass ratio plot with all the constraints at redshift 0. This is where the models lie. You can see there's a very clear break between the supernova model, which suffers from overcooling, forms too many stars. All the radiation pressure models are clustered nearby, and they're all within a factor of 3 of each other in terms of stellar mass, modulo the changes in the star formation efficiency, which may be important. Again, any deviations from this ratio, the observed ratio in this regime can be accounted for by the scatter in the observations here. The scatter that you see, these error bars, are only systematic errors. The other thing that I want to emphasize here is that the models with only supernova feedback have very low gas fractions, cold gas fractions. And you can see it in this plot over here. This is a cold gas mass or stellar mass compared to observations as a function of stellar mass. You can see that the supernova model in green here is very gas depleted, less than 1 in the ratio, and all the radiation pressure models are close, where although you start to see the differences between the different parameter choices and how much you overpressure the gas. In the baryonic Tully-Fisher relation, you may not see these differences as clearly, so you have the supernova model close to the fiducial radiation pressure model, so this relation might not be the best to compare to simulation, since it may be degenerate. So looking in detail at what the baryons are doing in each of the fiducial models, here's the supernovae model, here's the radiation pressure momentum conserving model. So this is the baryon fraction in each component as a function of radius. We can see that they look pretty much the same. So this is a new result. Many people say you need to eject most of the baryons out of the halo, and we see here that in order to get the right stellar masses, you don't have to do that. I think Piero also alluded to that. You have about the same amount of baryons within the Vero radius, but you don't have this concentration of baryons here within the galaxy, which observations tell us should be about cosmic mean, which is what we get in the model with radiation pressure. The only difference is that you're moving most of the excess stellar mass into cold gas in the model with radiation pressure. And if you keep this gas dilute, then you're not forming an excessive amount of stars. There's also slight differences in the amount of cold gas in the CGM as well, and you'll see how these make a difference. Here's what the distribution of mass within the galaxy looks like in terms of the circular velocity curves. Again, we see the signature of overcooling in the supernovae case, whereas in all the radiation pressure models, we get similar results, where the galaxy is dominated by dark matter and has a very slowly rising rotation curve. The baryons are always dominated by gas, with a very small contribution from the stars. Here's what a typical dwarf looks like in mass models, where they can actually constrain the contribution from the stars. And we see that all the terms are about right. The rotation velocity within, as a function of radius, is also pretty well reproduced by the models with radiation pressure. So here's how these galaxies grow. On the left, I have the dwarf models, and on the right, I have the M33 model. So I'll just focus on the dwarf model for now. We see that the supernovae model has runaway star formation at very high redshift of about 2, and then it sort of tapers off. 80% of the stellar mass is assembled by redshift 2. In the radiation pressure models, even though there's some spread here, this is mostly due to the assumed star formation efficiency. So you can see one thing: these models are all low in the stellar mass, as I told you before, but the star formation rate is low all the way to high redshift, and some models actually form more stars at low redshift after redshift below redshift 1. So they have increasing star formation histories, and this is one of the few times these are seen in simulations. So here's a more detailed comparison. This time I'm showing the star formation rate and the different models. Here's the star formation rate binned in broad bins of about 1 gig a year. And you can see, because this is the resolution of the best observations, and you can see how the supernova model has very high star formation rate that's inconsistent with observations. Here's observations of local group dwarf irregulars. You can see they're close to constant. And the other thing is, when you look at the star formation rate in detail, you see that some are more bursty than others. This should have a very important effect for the creation of cores versus cusps in the center of these dark matter halos. You can see in the distribution and the temperature density plane that the model with radiation pressure is depleting the amount of cold star forming gas here, although we still have some low levels of star formation. And most of this gas is moving here into the intermediate regime, and so we don't have as much hot gas as in the case with supernova feedback. This might be very important for what the properties of the CGM look like in absorption. So again, I'd like to stress out, it's very different to include the feedback in the form of pressure. So quickly, if you look at the properties of the outflows and the inflow, on top I have the distribution, the mass-weighted distribution of different gas at different temperatures in the supernova model inside the galaxy and inside the halo. And here I have the ratio of the fiducial radiation pressure to the supernovae case. We see a very large enhancement of about a factor of 10 in the warm gas outflows, and a decrease in the hot gas, as well as an increase in the amount of warm gas that comes back and is recycled. And finally, if you stretch out that plot as a function of radius, you can see that in the supernova model there's outflows to very large velocities, but very, very small mass. Not a lot of it reaches the virial radius. Whereas in the radiation pressure case, it's more bursty. Each of these is a burst of star formation that produces an outflow with a much larger mass loading factor. And you can see that the temperature of these outflows, this is only cold gas now, is much colder in the radiation pressure case. So this is one of the things that we're not expecting. So the outflowing winds are much colder once you include radiation pressure. So we do have, so we should be able to make predictions as to what the CGM looks like in absorption versus only supernovae feedback. And lastly, the last point that I wanted to make, I was just looking at this, is the density profiles of the dwarfs. And it seems like in agreement with Jose and Phil Hopkins' work that we don't see cores in our galaxies, even though the feedback is very strong and the star formation rate seems to be very spiky, very bursty. We don't see cores. So here you see a comparison with the adiabatic case, which is the profile that you expect to see without baryons. And here I'm plotting only to the radius at which you're supposed to resolve the density profile. Within that radius, you don't see any indication of a slope that's any shallower than -1, which is the NFW slope. So for dwarfs, we don't have cores, but perhaps for more massive galaxies, I'm not showing that plot here because it's preliminary, we might see an indication of cores. So these are results that are very, that are in contrast with what supernova feedback simulations have been saying. And here's my conclusions. I won't go through them, but I'd like to emphasize, again, radiation pressure produces very different galaxies. We reproduce the star formation histories from observations in the low mass star-forming galaxy regime. And we do not seem to be producing cores. And I'll stop there.
Good, good.
Can you go back to one slide? So if I read this correctly, then the halos are expanding when you put in the feedback. Because everything's above the black line.
No. So the adiabatic line is the orange. The black line is the supernovae feedback case.
Okay, so the dashed lines are above the orange line.
I'm sorry? The dashed lines are?
The modes with the radiation pressure feedback are above the adiabatic simulation, which means the halos are expanding.
There's no adiabatic simulation. Where's the adiabatic simulation?
That's right, the orange line.
It means above on the bottom plot.
Oh, on the bottom plot. It's possible.
No, it's not possible. It is what's happening. Anatoly, you created halo expansion. You created simulations with halo expansion.
I don't control it. It's
So yeah, it's a good point. I have to look at these in more detail because at first I thought the halo was contracting to some distance and then creating a core in the center. But I think I have to figure out what's going on. Again, the slopes are still not what is expected from the NFW fit.
The thing is that we know NFW is not the right answer, it's INASCO. So everything should be, even if you get a simulated -1, it means you're expanding.
That's a different story. Difference between the master and NFW is the 10% or 20%. Not a big deal.
Yeah, well, just going to follow up on what Aaron was saying. Maybe I'm just reading this plot. That red dashed line is almost constant within about 0.4, 0.5, doesn't it?
What do you mean constant? In the top here?
Radiative centimeters to -3 doesn't vary by more than a factor of few from 0.6 down to 0.2. That's very flat.
So you claim that's a core. I guess that's what
Well, I think that's as cool as anything that anyone finds. I mean, most of the cores
From
claims are really like where it's the -0.5 and you go to 6.
But the opposite in water is -1. Right?
the problem is that's right. The slope at
yeah.
But
there seems to be closer to -1.
well, but I mean, I don't. How does the bottom line follow from the top? It looks really flat. But anyway, I don't know. I mean,
I think it's hard to to see it there, but I can check that.
No, it's -1. It's a decay on that axis. It decays on that axis. It's -1.
It's
The density profile goes all the way in past 200 parsecs, but in the slope profile it stops at like 400. Right?
yeah, but you're looking at between 4 and 5, right?
Right, which is the point. We
Yeah.
Typical parsec size cores. We're talking about 400, 500 parsec size cores.
Yeah, typical cores start up around here, right, in this area. So you shouldn't really be looking at this. This is really not resolved.
Oh, I see, I see.
Yeah, so I'm cutting here at 200 particles, 200 dark matter particles within. So this is the radius enclosed in 200 particles. And you can see these extend more because, of course, these are more dense in the center. So.
It's not always the case of the slope piece. At least reduce the rotation if we modify this. Exactly.
Yeah, exactly. So one of the points is that how you define a core, and so you find different definitions depending on whether you ask a theorist or, again, you have the observations here, right? So.
I agree, I agree.
And I also would like to stress, I guess I would say, can comment on that. It depends on how you define where you're converging. So you guys don't like to go that deep in the profile because you think maybe there you're dominated by resolution effects. So it depends on, I think it needs to be agreed on how deep you can go.
There's
Right?
no course. What? No, if -1 is a cause, then it's all of them are cause.
Yeah, I'm cutting down to the overall radius, which is the number of particles that's not
How many particles do you have?
I think it's a technical issue now. I think because we're eating now, coffee break.
Yeah. Good job.
I think Adi had a.
Everybody.
I just wanted to comment
People don't want
that you said that your results are not consistent with core formation from supernova feedback to the gas seas. And I just wanted to say that at that virial mass range, what we find is exactly that. So an alpha of about -0.7 for that mass galaxy. So this
The thing is that it's tricky because it depends on whether you use stellar mass or halo mass, right? So there's.
Stellar ones, I don't think.
right, it depends on the stellar mass, but this is very, broadly consistent. You can look at
But it's. Yeah, but you're looking at a different radius.
No,
So.
between 0.4 and 0.5. The parsecs. So that's
Okay, but it is inconsistent with what I thought.
No, it's a different. See, it's a different burst mechanism.
Yeah, no, I know, that's what I mean.
It goes smoothly.
That's right.
You don't.
It depends, and it also depends on, when you start to create a core, when you create it early or not. If you start to create cores very early,
Yeah.
it's easier to
Yes, that's all.
enlarge
So it depends on
than
the.
doing very late.
This goes back to the star formation history, right?
So it depends on the stuff.
Where your star formation history picks where you have the most energy getting injected into the dark matter.